Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Hello and welcome to the MIT Faculty Forum Alumni Edition. I'm Joe McGonigal, Director of Alumni Education, and I'll serve as your moderator. A reminder that we'd welcome your questions during this broadcast. Use the chat form below the stream or tweet with MIT Better World, hashtag MIT Better World, and we'll get to as many questions as we can for our panelists. Today we're hearing from three alumni about the work that gained them acclaim from the White House's Presidential Early Career Awards for Scientists and Engineers. In its 20th year, this award highlights the key role that the federal government plays in encouraging and accelerating American innovation. I hope our guests will share some of their research today from their federally funded work and some of their thoughts on the research industry they're in and their career paths to date. But let's start with an overview of each of their research. Panelists, you might catch us up on your career since leaving MIT, and then talk about your current projects. And if we can, let's start with Professor Marco Pavone. He's Assistant Professor of Aeronautics and Astronautics at Stanford University. Professor Pavone, take it away.
Sure, thank you very much. So I received my PhD from MIT in 2010 from the Department of Aeronautics and Astronautics. And after my PhD, I joined NASA JPL, Jet Propulsion Lab, which is a center within NASA that deals with the robotic exploration of the solar system. And there I was working in the robotics section, working on Mars rovers and other type of robots for exploration of low gravity bodies, like, for example, asteroids and comets. I worked there for about 2 years, and then I moved to Stanford in 2012, where I joined the faculty in the Department of Aeronautics and Astronautics. At Stanford, I ran the Autonomous Systems Lab. Let me show you a few slides to illustrate my work. Okay, so the goal of my lab is to develop analysis, design, and control tools for the control of autonomous systems, which are robotic systems that are meant to operate in scenarios that cannot be foreseen at the design stage. In particular, by merging tools from machine learning, optimal control, and decision-making, I work on three complementary areas. The first area deals with the control of individual autonomous systems. I work on trajectory optimization algorithms for increasingly agile systems. I work on algorithms for the seamless integration between decision-making, perception, and higher-level cognition. And I work on deriving mathematical guarantees that enable the high-confidence implementation of these technologies in real systems. As a second area, I work on controlling networks of autonomous systems. In particular, I focus on transportation networks where mobility is provided by self-driving vehicles. And in terms of application domains, I focus on aerospace robotic systems, like, for example, drones or space robots. And as I said before, transportation networks where mobility is provided by self-driving cars. The overarching approach of my research is to leverage optimization-based control, which entails the online, that is real-time generation of optimal control inputs for the feedback control of an autonomous system. And the idea is that the changes can be made to the cost function in order to reflect changes in mission requirements. Changes can be made to the constraint sets in order to reflect changes in the environment. And changes can be made to the parameter set in order to reflect changes in the capability of the robot. The idea is that, and the key advantage of this approach is that a robot can adapt to a wide range of possible scenarios. Now, I don't want to go into the mathematical details of my work. I'm going to show you a few highlights of my research, primarily in the context of aerospace vehicles, which is the research that gained me the PK's award. So as I said before, I work on trajectory optimization algorithms for autonomous systems. So here I'm showing you the application of these algorithms to 3 robots that free float on a very flat granite table in a way that emulates their dynamics in a reduced gravity environment, for example, around the Earth in orbit. Here you are seeing a robot that is computing a number of trajectories portrayed in yellow. And as you can see, the robot constantly recomputed trajectories in order to counteract disturbances and achieve a successful dock. So this work that I carry out in collaboration with a variety of NASA centers, like, for example, the Goddard Center and the Johnson Space Center. Another work that I have in collaboration with NASA entails manipulating objects in space. The key difficulty of manipulating objects in space is that if you're not careful, when you contact an object, the object drifts away. So it's very hard to catch it. So what we're leveraging are new materials that try to emulate the sticking properties of the gecko feet. And here you can see in this movie how with this gripper we can grasp quite reliably objects that could be potentially be much larger than the spacecraft. And the idea with this gripping system is that we reduce the problem of grasping that traditionally is quite complicated because it entails coordinating several joints in a robotic hand to a much simpler problem of docking. Another project, still in collaboration with NASA, in particular JPL, entails designing robots for the exploration of very low gravity bodies like asteroids and comets. To give you an idea of what low gravity means, let's assume that I had to pick Joe and let him fall from a height of about a meter. It would take him about 2 minutes to reach the surface. This means that we need a completely different mobility systems in order to cope with the lack of gravity. So let me show you a movie that illustrates that concept.
Comets and asteroids are very fascinating places. They may contain building blocks or the remnants of the building blocks of the solar system. However, to explore, but they present a unique set of challenges. There is the low gravity environment, or microgravity as we call it. For example, a person here on Earth would weigh as little as a paperclip on the surface of a comet. So rover like Curiosity, which is currently exploring Mars, would actually only weigh a couple of kilograms. It wouldn't be able to generate much traction. And in fact, as it turns its wheels, it would probably just push itself away from the surface. It's actually quite likely to end up rotating and landing upside down, at which point it's ended the mission for the rover. So instead, together, JPL and Stanford have been working on a totally different rover concept that is well suited to these environments, called Hedgehog. Instead of rolling around on wheels, the Hedgehog design actually puts 3 flywheels on the inside of a cube. By spinning these flywheels up very slowly and then very quickly applying a brake, which transfers all the momentum from the flywheels, we're able to cause Hedgehog to either hop or tumble or perform small adjustments. So we've done many tests here on Earth in gravity offloading test beds. Recently, we've flown 2 Hedgehog prototypes on a zero-G aircraft. In these tests, we demonstrated that we would be able to perform on a comet or an asteroid. Hedgehog doesn't have a right way up. Instead, it can tumble over the surface and come to rest on any one of its faces and still work perfectly. The Rosetta mission has sent back lots of very fascinating images from the surface of Comet 67P, and these images show us some incredibly rugged terrain, including large sinkholes where a traditional rover would get terribly stuck. So we've even tested Hedgehog performing a type of escape maneuver, where it spins itself up and does this tornado-like maneuver where it can actually launch itself vertically out of the sandpit. In our future work, we're looking at increasing their level of autonomy, giving the Hedgehog rovers the ability to think for himself and to navigate from one point to another. The Hedgehog rover's ability to move around on the surface of comets and asteroids could enable a wide range of applications and science in the future.
And finally, the decision-making algorithms, the trajectory optimization algorithms that are developed for space applications can also be applied to other type of agile autonomous systems, like, for example, drones. By the way, here is a picture with the NASA administrator at the US Senate holding some of our platforms. The one on the left, it's me. The one on the right is one of my students, and the person at the center is a NASA administrator. So I was saying that my work can also be applied to other type of autonomous systems, for example, drones. Here in my final slides, you can see one of my students fencing with one of the quadrotors that is controlled by using my trajectory optimization algorithms. We are currently working on equipping the drone with a plastic plate and let the drone engage with a human. We want to do this, one, because it's cool, but two, because it allows us to validate our models and algorithms for autonomous human-robot interaction. In this context, in an adversarial setup, but that could also be applied in other setups, for example, for self-driving cars, when you want to achieve coordinated lane changes or very smooth negotiation of intersections. And I will stop here, and I'll be happy to answer any questions you might have.
Thank you, Marco. And we've got a couple questions coming in already about that. But let's get to our other panelists here for a brief overview. Jelani Nelson at Harvard. How about your work and your progress to date since leaving MIT?
Sure. I'm afraid I'm not going to have any cool videos, but I'll just speak about that. So yeah, I went to MIT as an undergrad. I graduated in 2005. I was 6 and 18, meaning double major in computer science and math. I lived in Bexley, which unfortunately no longer exists. I stayed at MIT for my MEng for an additional year in computer science. And then I did my PhD also at MIT. I graduated in 2011 in computer science. I was in the theory of computation group at CSAIL. And my final year of grad school, I accepted an offer to come here to Harvard, which is where I am now. That was in spring 2011 as a faculty member in computer science. But I deferred it for 2 years to go do research elsewhere. So I spent a semester at MSRI, the Math Science Research Institute in Berkeley, California. And then I spent a year and a half between the Princeton Computer Science Department and the Institute for Advanced Study, which is also in Princeton, but not part of the university. So I can tell you a little bit about my own research. So my most general area is the theory of computation, which is modeling computation mathematically and proving theorems about what can and cannot be done or how efficiently it can be done, in those models. And more specifically, I work in algorithms, and algorithms is answering what can be done. So coming up with efficient procedures to solve computational problems, where efficiency might be measured as memory efficiency, use as little memory as possible, or time efficiency, run as quickly as possible to solve some problem. My work, my own research, deals with large and high dimensional data sets. And what we want there is to have algorithms that can process these kinds of large and high dimensional data sets efficiently. So let me give you a few examples. A good chunk of my work resides in the area of streaming algorithms. Okay, so there the model is there's a stream of data that's coming in. Okay, so for example, queries coming into a search engine, or packets coming into a router that then have to be routed. Okay, so there's a stream of data that's coming in, and what you want is the algorithm to process that data on the fly, process the stream on the fly, using very little memory. In particular, much less memory than what's required to actually store everything you saw. Okay, and still be able to answer queries about the data without storing everything. So, for example, one problem that I've worked on is something called the distinct counts, approximate count distinct, or distinct elements problem. And the idea there is, there's a router, there are packets coming in with, source IP addresses, okay, like the ID of the computer that's sending the packet. And what you want the router to tell you is, over the last hour, let's say, how many distinct IP addresses sent traffic, on this link. Okay, so how can you answer that question using very little memory? So much less memory than storing all the packets, much less memory than remembering, how many different IP addresses are there? There are about 4 billion of them, 2 to the 32. You don't want to use 2 to the 32 memory either. Okay? You want to use very little memory and still be able to answer this question. So that's the kind of question I've looked at, as well as kind of frequent items problems. So again, you're a search engine, words are coming in, these are search queries, and you want to know kind of what are the popular words that people have been searching for over the last hour? Or what's been trending, meaning if I look at its frequency, the frequency of a word being searched today versus yesterday, which words have a large difference in their frequency? So maybe that word is not necessarily the most frequent item, but if you look at these differences between two time periods, there's a large difference. Okay. So that's the flavor of problem for kind of the streaming model. And the high dimensional version, so I also mentioned I work on high dimensional computational problems. There the idea is, in some areas, like for example, machine learning, the idea is you have data elements. So for example, let's say I'm Amazon. Each data element is a user, okay, a customer on Amazon.com. And I will model a user as a high dimensional vector, okay? So for each user, I'll remember many features of that user. And a feature can be, what do I estimate their age to be? What time zone are they in? If I gave their, what's their rating between 0 and 100 of how much they like romance novels, et cetera, okay? So there are many features that I might try to estimate about that user, okay? And each feature is a dimension, so I'm a dimension of that user. So I'm imagining that they're very high dimensional because there are lots of features that I know about that user, or that I estimated about that user. And now I want to be able to solve problems on these high dimensional vectors, like recommendations, product recommendations, right? So given that I have all these users in my database, for this other user, like, can I estimate how much they would like this particular book or this particular product that I'm selling? What should I recommend for them to buy? And if I can do a good job at that, I can make more money. So algorithms for these high dimensional data sets. In particular, one thing I've worked on is dimensionality reduction. So how can you take in high dimensional data sets and kind of in a pre-processing phase, reduce their dimension in such a way as to guarantee goodness of the algorithm on the lower dimensional version of the data set. So provably, if I can solve the problem on the lower dimensional version, can I say that that implies a good solution to the original high dimensional version of the problem? So for example, clustering users or other kinds of high dimensional algorithmic problems. So that's I'll leave it at that.
It's probably some good intel for data on asteroids too, I imagine. But maybe we'll come back to that. And let's hear from Jenny Yang at University of California, Irvine. Jenny is an assistant professor of chemistry at UCI. And Jenny, welcome. Could you tell us a little bit about your current projects, your research, and maybe a little bit about your career path since MIT?
Sure. Yeah. First of all, can you hear me okay?
Yes.
Okay, great. So I apologize for being late. I have time zone problems all the time where I'm confused about what on my calendar. So basically I graduated with my PhD from MIT in 2007 in the chemistry department, working for Dan Nocera, who's now at Harvard. I then went and postdoc at the Pacific Northwest National Lab, which is the Department of Energy lab in Eastern Washington. And then I was basically hired as a scientist after my postdoc at the Center for Molecular Electrocatalysis, which was a new initiative there by Stephen Chu. I worked there for another 3 years, and then I moved to Caltech as a scientist at the Joint Center for Artificial Photosynthesis, and I was there for 1.5 years, and then I joined the faculty at University of California, Irvine in 2013. So that's sort of my story. I was at many national labs. I thought I would never be a professor, and then an opportunity came up. And so I took it, and so I've been going through that for the last couple of years. I can talk briefly about my research. I just mostly, I didn't want to be too technical, but I sort of wanted to give the motivation behind what we're doing. So the way that I can do that is I can screen share just sort of some slides from talks that I give more often to the public. I haven't used Google Hangout before, so I'll give this a shot. There's a way to share my screen, right?
The green icon on the left.
Okay, great. Okay, perfect. Okay, let me see here. Okay, here we go. Okay, I hope you can see that.
Yep.
Oops. Okay, so basically, we are working on renewable energy, but not in the sense that we're trying to make a better wind turbine or a better photovoltaic, which is I think what most people in the area do, or more energy efficiency, which are all really important things. Essentially, we're more interested about energy storage. And so this graph here I have for the Pacific Northwest, which is where I used to live, basically showing for 1 month, each day is a line. And it shows you solar, which of course only is generated during the day, and wind, which is very variable depending on how windy it is. And then the thick lines represent sort of the average over the month. And then in red is demand. So you can see that red demand for energy is relatively constant, but solar and wind are very intermittent, and solar predictably intermittent, right, just during the day, and the wind is not at all very predictable. And so because of this, there's a temporal discrepancy between renewable energy supply and demand. And so there's been a lot of articles written about this since I started my independent career. So right when I started, it was this New York Times article about the intermittent nature of green power as a challenge for utilities. Germany is running into this problem as they increase their share of renewable electricity. Solar energy is growing fast, but nighttime is still a problem. Very recently, last month, in this article. And that's sort of why there was this article in Forbes last year that said why energy storage may be the most important technology in the world right now. So that's something that we're interested in. And so I think Tesla is trying to basically address this problem right now by using batteries, which I think is really great. And I think there's a lot of good research going on in that area. But one of the things that we wanted to look at is really, if we think about energy storage in terms of by density, by volume, and by weight, you can see on this graph here that lithium-ion batteries, according to this scale, at least as currently commercialized, are not very energy dense by volume, by weight. So what sort of fills in this graph at higher densities is basically chemical bonds. So any chemical fuels, diesel, gasoline, jet fuel, you can see body fat on there, kerosene, you know, all these things are very energy dense compared to batteries. And so, as I said, Stephen Chu was sort of my super boss when I started at a national lab. And so he asked this question a couple years ago to sort of highlight this problem or the solution. And he basically said, you know, what does a Boeing 777 and a Bar-tailed godwit have in common? He actually asked the internet this, and I thought it was a great question because it illustrated a very good point. It's not that they both fly, but it's related to that. Essentially, they can go 7,000 miles without refueling, and it sort of highlights how important chemical fuels are for transportation. Because if you need to carry your fuel with you, it can't be either bulky or heavy. You want to get the highest density as you can in order to basically not have to refuel very often. And so, you know, the plane can go from LA to Sydney in one go over the Pacific, and then this bird goes from Alaska to New Zealand. And so essentially, this is the storage of, for example, solar energy in the form of chemical fuels. I'll just put that on the graph there. This the bird obviously uses body fat, and the Boeing 777 uses diesel or jet fuel, I guess, is a more accurate representation of that. And so the idea behind this is, you know, this is actually what happens in nature. All the fossil fuels that we use now are the product of photosynthesis over eons. And essentially, the field that I'm in is basically often called artificial photosynthesis, which is instead of using sunlight or basically replicating what plants do of using sunlight to make chemical energy. And so we replace the light absorbers in a leaf with a photovoltaic, and then we basically drive the electrolysis or uphill reactions using that energy to store that in the form of chemical fuels, whether it's hydrogen or reducing CO2 to hydrocarbons, basically making carbon neutral, carbon-based fuels in that way because they're generated using renewable electricity. So that's sort of the field that I'm in. We focus on the catalysis. I didn't want to talk too many details about that. I'm happy to answer questions, but essentially we make catalysts that can use electricity to reduce water to make H2. We're also trying to find ways to make CO2 reduction, both to CO, which is energy rich and can be used in Fischer-Tropsch reactions, formate, which is an H2 carrier, and sort of our ultimate goal at this point is basically to make those hydrocarbons or things that precursors that can easily be made into hydrocarbons that can then replace fossil fuel sources for transportation applications. So that's our approach, is basically using synthetic and heterogeneous catalysis to do that. So that's sort of the quick overview of what we're doing, and I'd be happy to take questions on that. How do I turn?
Thank you, Jenny. Yeah, and just hit the green again. Let
Okay,
me
there you go.
let me try to aim at questions from viewers that are at least addressing a couple of you at a time here, and maybe I'll forward everybody's questions at the end. But Jenny, if you could start, and maybe Marco, you can chime in too on specifically on automobiles and cars. Jenny, how far away is a hydrogen fuel powered car? Asks one viewer. Marco, you might have an opinion on that, or Jelani, but also Marco, to address autonomous vehicles, we might as well mention too.
So for hydrogen power, they exist. I've seen them at various shows. They have them with compressed hydrogen in the back. The hardest part about a hydrogen powered car is the storage of the hydrogen and refilling it. So right now, all the, I think, prototypes have compressed hydrogen. There's basically no way to store it in a way that doesn't require a compressed tank that's easily refillable. And the DOE did spend about 10 years trying to find better ways of doing that. And basically, because it's a gas, it's just not very compatible with our current fuel infrastructure. And so the idea is that hydrogen would be fine for remote applications, but maybe for a car or something, we'd like to try to get a liquid fuel, because then it could just sort of plug into our current system.
Good. And Marco, I don't know if you want to weigh in on that, or just to tell us about lessons you've learned about or lessons you're thinking about autonomous vehicles on Earth as you design, Hedgehog for asteroids. Are you looking at Hedgehog and saying, gosh, that would really inform the discussion on autonomous vehicles right now?
Well, the Hedgehog platform is designed to move on very low gravity bodies, so will be very inefficient on Earth. But on the other hand, the algorithms for decision making that are used to control the Hedgehog could be applied, and indeed are applied, for the control of self-driving vehicles. And indeed, I also have a fairly major program in terms of control of autonomous cars that I didn't mention. And coming back to your question about how far along we are with the development of autonomous cars, autonomous cars come in a variety of different types, with different level of supervised autonomy to complete full autonomy. I would say that fully autonomous car that can move at fairly low speeds in a semi-structured environment, like for example in gated communities and so on, are quite close. I would say in the next 2-3 years, we could see already some deployments, for example, in military bases, or as I said before, gated communities and so on. Most of the people working in this area agree that by 2021, 2022, depends who we talk to, we might start having deployments in terms of vehicle moving in normal traffic, like for example, highways or certain roads, with an outline that stretches all the way to 2030. So they could be quite close. Of course, there are a number of issues that still have to be faced. I'm not saying it's easy, but it's doable to get to a reliability of, say, 98, 99, 99%. Dealing with the corner cases that last 1% that makes the technology safe is still quite challenging, and it's still quite a bit of work to do. But having said that, I would say that technology is quite close to being infused in applications, which is exciting, but also raises some issues. For decades, people have been talking about the impact of automation on the labor market. Well, by automation, I mean robots that can carry out very repetitive tasks. Now, with autonomy, we might start considering what the impact of cognitive robots could be on the labor market. So this is yet another challenge that probably engineers, economists, sociologists together should start working on.
I don't know how many of you read the New York Times editorial today about robots in your job.
Yes.
But
yes.
the
there is an increasing number of articles and studies about this topic. Elon Musk had an interview a few days ago, same thing for Bill Gates. But many confuse in a way the concept of automation with autonomy that, in my opinion, are quite distinctive. Here, not only we're going to replace a repetitive task, but possibly also cognitive tasks.
Yeah, it's a nice segue into somebody provided the link to the Chronicle of Higher Education. Had this interview with MIT's own Eric Brynjolfsson this weekend at AAAS, talking about the job of the research scientist might fall prey to automation as well. I wonder if any of you have thoughts on that. But the academic research scientist examining large data sets may be, a victim 5-10 years down the line of computerized automation. Jelani, does that keep you up at night?
No, not at all, actually. Because so I'm a theorist, right? And I guess we theorists know that the task of proving theorems is undecidable. So what that means is that there does not exist an algorithm that's guaranteed to always terminate. That given a statement can find you a proof of whether it's true or false. So you cannot automate this. Of course, people still try to come up with theorem provers, but they can't work in the general case. That's a mathematical fact. Right. So, yeah. I mean, I guess the question is, can you? So then, in terms of like proving theorems, humans, we have something which we call like creativity, which tries to find new ideas and evaluate them and find find proofs of various mathematical theorems. Well, do I expect creativity to be automated in the near future? I don't, not really. I mean, maybe they can comment on how far along we are in automation. I don't see creativity as being near the level of being fully automated right now and competing with humans.
Yeah, and agree. I would like to make the difference between the field of autonomy with the field of artificial intelligence. When you control a self-driving car or when you control a drone and so on, even though sometimes engineers like to use flashy names for the algorithms they develop, I wouldn't claim any creativity skills are deployed on the robots. The robots still run a program that performs within some requirements. Autonomy is still very much a requirement-driven science, as opposed to the larger field of artificial intelligence that tries to tackle the much more general question of whether the human mind in all its different facets can be created. And for that, I have the same concerns that were mentioned before. Algorithms for decision-making, for perception, for elaboration of data are nowhere near to achieving those skills, in my opinion.
Let me jump to a question. It's Noah in San Diego says, and let me broaden it to at least two of you again. Is your work having relevant impact on the developing world? And how much do you, Jenny or Jelani, how much do you think about either renewable energy in the developing world through your work, or Jelani, how much will sensor networks and will the smart home impact the developing world, or getting faster streaming of video and so forth, thanks to improved algorithms? Either of you want to pick up on that?
I mean, I'll say something at first, which is not exactly answering the question, but it's something related to a hobby of mine, which is something I did even last summer. This is not the impact of my research on the developing world, but just something that interests me. So I guess one thing I did right after I finished my PhD, before I started the postdocs, I went to Ethiopia, where I have a lot of relatives, and I spent 6 weeks there. And I thought to myself, I'm going to be here for 6 weeks. That's a long time before I start my postdoc. I I want to do something more than just see my relatives every day and hang out. And so I taught a class, an algorithms class, to high school students in Ethiopia, in the capital city, in Addis Ababa. And there was a 4-week program. It was pretty intense. They were like we met 2.5 hours a day, 5 days a week. And when it was over, a lot of the students had like no programming experience. And when they came out of it, a lot of them became very interested, and some of them even applied to schools in the U.S. A couple went to MIT, one's at Harvard now. Several went to several other schools in the U.S. as well and abroad. And that's something that I partnered up with an organization in Ethiopia for the second time around. That was 2016, last summer. Now I'm busier. I'm a faculty member. I do research, et cetera. I don't have time to spend 4 weeks teaching high school students anymore, unfortunately. But I found some other teachers, and I myself taught for just 1 week of it. And we did it again, this time bringing students from all across the country as opposed to just the capital city. So, I mean, I do think about, I guess I haven't thought a lot about my research and its impact on the developing world, but I have thought about just things that each one of us can do to bring more people into the field. And in my case, what that was just going out and kind of evangelizing algorithms and computer science to a lot of high school kids who might not have been exposed to it, at that age.
Good. And Jenny, you want to weigh in, or?
Sure, yeah. So I would like to think that this way of utilizing energy would have a big impact. And, they're not just all my ideas. My former advisor who got me into this field of research basically is the one that sort of really put in my head that this is really an opportunity for the developing world to accelerate their economies very quickly. So I think the analogy that he used to use was in developing countries, they have never had to put in landlines, right? They just went straight to cell phones, and that sort of skipped that whole infrastructure and basically use the best technology out there. And I think when it comes to energy, it's even more impactful because everybody has access to solar. I mean, if countries like Germany that are way up north can supply most of the electricity through solar, we know that, certainly countries further south, closer to the equator can certainly do it, or through wind or through tidal. And so this is a way for countries to access these resources that instead of relying on other countries for them, and also for developing an infrastructure for renewable energy without having invested in all the old infrastructure, right? So I think I've heard that it was an astronomical number that I can't remember about the amount of money that's been invested in fossil fuel infrastructure. And if you could skip that and everyone has a solar panel on their house and a way to generate carbon neutral fuel, then it becomes personalized, right? So everyone can basically generate their own energy. They don't need to rely on giant power plants or fuel refineries, transportation, and pipelines and all these things, right? You can basically skip all that and go straight to everybody generating their own fuel and electricity. So I think it's very powerful in that respect because I think it is a way, sort of very much like communication, skipped over the landline in developing countries, that the energy can go straight to renewable and skipping over all the pipelines, refineries, and all the other infrastructure. So I'm very optimistic, and I think that's why actually a lot of developing countries are interested in investing in this technology.
Good. Well, about 5 minutes left here, and let me encourage panelists, if you have a question for each other and you want to stump one another, let me know. But let me try to tie two other questions together in the interest of time and say, could any of you talk about intellectual property and your thoughts on patents and on publishing? You could even just talk about your experience in publishing in 2017 and what that's like versus 10 years ago or 20 years ago. But patent disputes plaguing academia, this one viewer has asked about. Anybody want to take that up and talk about intellectual property in general and your particular field, and how much you think about how much that weighs on your day-to-day.
Well, I can start. Certainly, IP for my field can be a challenge, especially for my work related to self-driving cars and drones. The Silicon Valley is bubbling up with startups working in these domains. So any algorithmic advancement that you make there might have a monetary value. So the way that this impacts my research is that when I set up a grant with a company, I had to educate the company in what research really is, which means essentially foundational concepts that are going to be publicized with the world community of scientists and engineers. And that takes some effort to convince them that there is value in investing money in this type of work. But especially large companies are quite receptive to this model. For example, I have projects in collaboration with Toyota, Northrop, Qualcomm, and so on. Of course, the companies have the concern that some of the data that they make available might be included in papers, and so there might be some leak of IP proprietary data. So the way it works is that usually when I submit a paper for a project that is sponsored by a company, upon submission, I send the paper also to a company, and I give them a few days to check whether there is some data they would like to keep confidential. But that rarely happens. So to make a long story short, I would say that the IP patents are not really impacting my research in any significant way.
And Jenny or Jelani?
I guess I can go. Yeah, it hasn't impacted my research really much either. When I was a student in summer 08 and summer 09, I spent those 2 summers at IBM Almaden Research Center in San Jose, California. And some of the work that I did there, I think, ended up into IBM patents. That was all handled by people at IBM, like their legal team and maybe some of the full-timers who were mentoring me. But that did not block any publication of what I was doing. They have a pretty nice research culture there. And I guess subsequent to IBM, I never pursued patents on any of my own work. I learned when I was at IBM that you apparently you can't patent an algorithm. You have to patent, the application of an algorithm to a specific problem. And my work is, I guess, theoretical enough that I really do focus on the algorithms more so than the applications, and so I haven't really pursued that direction thus far.
Jenny, anything to add?
I'm a big proponent of open source publication, especially for federally funded research. My feeling is the taxpayers pay for it, and they should be able to access our research for free, or the results of our research for free. I also think it's important for developing countries to be able to access other research, right? That's how science is founded, is by building on other people's work, and they shouldn't be limited in whether they could afford to access what's been done in the field. For patents, I would say that my research, although I sort of gave you the motivation behind it, is very fundamental. And so we do talk, there are actually quite a few companies in Asia that are interested in investing in basic research in this area in other countries in the US. And we think that's great, that they are willing to put money into things that, have a 10 or 20 or 30 year timeline. But the intellectual property is something that has really limited that. And I guess I'm not a lawyer, so I don't deal with that in my university, but I know that it's an issue, even though the things that we do, like I said, don't have direct applications. But I do think it's important for scientists, even ones that do fundamental chemistry like myself, to continually talk to industry, because I think it's a very good way for us to think about applications and whether the science that we're doing will have an impact in the areas that we want them to in the way that we want them to.
We've gone over our time and gotten to about a third of the questions, so I apologize to those we didn't get to. But I want to thank our panelists here. We got tip of the iceberg of your research, really, in our discussion today. And thanks to our viewers for tuning in. This has been Faculty Forum Online, Alumni Edition. Thanks again to our alumni panelists from Stanford, Harvard, and UC Irvine. We will forward the questions to the panelists if they have time to answer them. And you can share tweets about today's broadcast using MIT Better World, and send any feedback or follow-up questions to alumnilearn@mit.edu. And thanks again to our panelists, and thanks for watching.
Thank you very much.
Thank you.
Thank you.
Bye-bye.
Thank you.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.